Welcome to second steelmaking course, lecture 22 unit 5. The unit 5 mainly consists of numerical problems from steel making, thermodynamics of steel making, secondary treatment, secondary steel making, casting process. All those problems are included. So I will take one of the numerical problem today. That is, the main problem was, consider the deoxidation of molten steel aluminium at 1600 degrees Celsius temperature. The molten metal bath contains 1% of manganese, 0.1% of carbon, and the oxygen was brought down by the addition of aluminium was 0.001. everything is in weight percentage and the remaining is iron. Now one need to do the aluminium addition was done by solid strips or wires. The aluminium is going interacting with the molten metal bath, aluminium oxygen form, and which has higher melting point than the steel above 1600 degrees Celsius temperature is having with Al2O3. Immediately the Al2O3 form of semi-solid comes to the top. That particular aluminium is reducing the oxygen dissolved in the molten metal bath, steel bath. What is the amount of aluminium is gone out? How much aluminium is retained was the main question. Calculate the residual aluminium content of molten steel assuming the equilibrium reaction is happening. The aluminium and oxygen is reacting. 2Al, 3 oxygen is giving rise Al2O3 form of semi-solid droplets. And another given data is from the thermodynamics, log of, from the free energy equation, log of equilibrium constant aluminium is minus 58473 by T. The T is in degree Kelvin. It is given degree Celsius. You need to convert into the Kelvin. You need to substitute here. Plus 17.74. And another values are given. Interaction parameters between aluminium and manganese, aluminium and carbon, aluminium and oxygen, and aluminium. Another interaction parameter with oxygen, oxygen manganese, oxygen carbon, oxygen oxygen, oxygen aluminium. These values are given. Now you are supposed to calculate what is the weight percentage of aluminium retained after removal of 0.001 weight percentage of oxygen. Is the problem. I think it is clear. Now I am going to explain the solution. The Al2O3 is 2Al and 3 oxygen. This is in the equilibrium. Now because this particular aluminium is dissolved in the molten metal, oxygen is dissolved in the molten metal, this is going as a slag. You need to apply for these two Henryan law for this Raoult's law. That is, when you apply, when you rewrite with the equilibrium constant of aluminium, this becomes like Henryan's H of Al, since it is 2 square, H of O cube by products, reactants and products, Raoultian activity of Al2O3. And assume that since this particular Al2O3 is single component going out as a slag, and which can be easily removed, assume that the A of Al2O3 equal to 1. Another condition. And now it becomes, this is 1. So finally equilibrium constant with respect to the aluminium, retained aluminium you need to calculate, residual aluminium. This is the final equation. And this can be rewritten. This is Henryan coefficient F of Al and weight percentage of aluminium. It is been further simplified, and for calculating this particular Henryan coefficient, there is a relation equation given between the interaction parameter and Henry coefficient. The Henry coefficient of aluminium is given aluminium manganese weight percentage of manganese, aluminium carbon weight percentage carbon, aluminium oxygen weight percentage oxygen, and aluminium weight percentage of aluminium. And these values are known. We know manganese, we know carbon, we know oxygen, and we do not know aluminium. So and even this interaction parameters also known. Substitute, finally you will be getting the log of AFL is equal to 0.0025, and when you can remove this particular log, that is 10 to the power of 0.0025 becomes 1.006, that is FAL value. This value you can substitute there. This is 1 point is calculated. Now coming to similarly oxygen, Henry coefficient with respect to the oxygen. For that again equation between the interaction parameter and Henry coefficient is given like this, and when you substitute all these particular things with making unknown value, you will be getting this value minus 0.0662, and when you remove the log, it becomes FO equal to 0.859. And as we know, the temperature was given 1600 degrees Celsius molten metal temperature, converting into the Kelvin, and this equation also given. So you can calculate this particular KL, left side KL. This is for right side, you calculated these values and you can substitute in the equation 2. For the left side, you will be calculating from this free energy equation log of KL. By substituting the T value 1873, it will come minus 13.48, and when you remove this particular log, that is 10 to the power of minus 13.8, that is K of AL value, that becomes 3.32 into 10 to the power of minus 14. From second equation, this KL equal to this much, and we know this Fi of AL calculated, and weight of AL we do not know, F of O calculated, WO also is given, and only this KL also from the free energy equation calculated. Now everything is known, only unknown value is weight percentage of aluminium. The weight percentage of aluminium, this can be rewritten, simplified, and you can rewrite like this, and you can remove this particular square, and finally this particular value, the residual aluminium content is 7.193 into 10 power minus 3 weight percentage. This much steel was retained, and respective to the, it could be the gate examination, our end semester examination, 1 point you no need to solve entire. If it is the large question, 10 marks question, you need to solve all these particular things, remembering those interaction parameter equation, those simple relations. Otherwise it will be asked part of the entire problem. So you need to try to solve similar numerical problems, many from the SK Datta textbook. One is clearly I explained in this video lecture. Please understand. Thank you.